We will take a very simple example of how we can apply the Fulkerson algorithm for finding disjoint ST paths in both directed as well as undirected graphs. So we take a very simple example from the reference book Algorithm Design by Kleinberg and Tardas. So first we'll take the directed graph, and after that we'll take undirected version and solve both problems using Fulkerson algorithm. So just consider this example. We have source S, and then further nodes are V, U, X, Y and Z. X, Y and Z with T, and we have directed edges S to V, S to X, S to U, then we have V to X, V to X, V to Y. Then U to V, U to T, then X to Z, X to Y, Y to T, then Z to T. Then we have Y to U. So this is the directed graph. So first just imagine that each we convert this input graph into flow network with capacity 1. So just imagine that each directed edge has capacity equal to 1. Now we apply Fulkerson algorithm for this input. So initially we have flow equal to 0, and we make the residual graph, so it is identical. So this is our initial G as well as the residual graph GF when F is 0. So just to save my time and space, I will show the flow in this original diagram itself, and any modification of residual graphs I will draw them separately. So initially we have flow equal to 0, and this is also the residual graph. So first we have to find ST path and then augment the flow. So we can find the path. So there are several possible paths. We can choose any one. Take for example this. We go from we can either choose S, X, Z, T. There are several possibilities. S, V, X. So there are several paths. We can choose any one. So let us choose like this SX SVX Y and T. SVYT we choose this. So bottleneck is 1 and we make the residual graph. So flow along this path will become 1. Make the flow equal to 1 and make the residual graph. So again we will redraw it. S V U then X and Y, then Z and T. So first I will make the back edges, then forward edges. So back edges are T to Y, then Y to V, then V to S. Then remaining are identical. S to X, forward edges, S to U, then from U to V to X, then U to V, U to V, U to T, then Y to U, Y to U, X to Y, X to Z, and Z to T. So once again we have to find simple S to T path and augment the path. So now also we have several possibilities, like for example S to XZT or S to UT or S to UV, S to U, UVX, ZT. Several possibilities are there. We can choose any one. So let us choose SUVXZT. So SUVXZT. So again bottleneck is 1. We augment the path, create a flow, SU, then V, SUV, then X, then X, then Z, and then T. Now we again redraw our residual graph with the new flow values. Call this flow initial flow. Initial flow, call it F0 with 0, then F1, then F2. Now again we redraw S U V X Y Z, X Y Z and T. So I will first make the back edges. They are from V to S and U to S. V to S, U to S. Then V to U, V to U, then Y to V, Y to V, then X to V, X to V. So we have considered these three and these two, 3 and 2, 3 and 2, and this 4 values, Z to X, Z to X, T to Z, T to Z, then T to Y. These are backward edges and rest are forward edges. So forward edges, these are as it is, S to X, then we have what is remaining is X to Y, X to Y, Y to U, X to Y, Y to U. Then remaining is U to T, U to T. So once again we have to find S to T path and then augment it. So now starting from S, we have only one choice, we have to move to X. At X we have two possibilities, either we can move to V or we can move to Y. So we can consider each case one by one. S to X, X to V, V to U, U to T. This is one path. Other can be, if we try alternative, S to X, X to Y, V U T or Y T. So again there are several possibilities. We can choose any one. So we can take for example X, Y and U T. So we take S to X, X to Y, Y to U, U to T. Take this path. So first I will mark the flow. Once again bottleneck is 1 and we have to increase the flow equal by 1 along S to X, S X Y U T, S X Y U T, S X Y U T. Now we make for this flow, call it F3, GF3 we make. So once again I will draw the backward edges first. So if we consider here, all edges are carrying flow. S2, so all, just we have to reverse the direction of all the edges and we get our final diagram, the residual graph. S UV UV XYZ X Y Z and T. Just reverse the direction of all the edges and we get our final residual graph. Since after that we cannot find any ST path because all edges are incoming to S now. So now we get all backward edges V to S, U to S, X to S. Then Y to U, V to Y, we make this V to like this. Just we check this is in the wrong direction. I will just correct this. So all incoming on S, then we consider V. So U, V to U we get, if we compare this original diagram, we have U to V, so V to U we will get, V to U we get. Then all are incoming on S, we have already drawn. Then we have Y to U, so we will get U to Y. U to Y. Then we have V to Y, Y to U, Y to V, Y to V. Then X to Z, so Z to X, Z to X. Then we have X to Y, so we get Y to X, Y to X. We consider V and X, V to X, so we get X to V, X to V. Next we consider this Y to T, so T to Y, T to Y. We consider Z and T, Z to T, so T to Z. Then U to T, so T to U. So now we have all the edges if we compare with the earlier diagrams. Now we can easily see there is no S to T path because all edges are incident on S. So now we get this final flow value. Its flow value is 3. Flow out of S is 3. So now only thing is we have to recover the disjoint paths. So we start from S, just follow the edges with flow equal to 1 until we arrive at T, or if we arrive at if there is a loop, we have to remove the loop. So just to explain how loops are removed, I will first choose a path with a loop, then see how we can remove the loop without affecting the max flow, and still we can recover the ST disjoint path. So we start from S. Here we have 3 options. We can move to X, V or U. So we choose V. After V we choose X, then Y, just to make a loop, V, U and V. So this is making a loop. S to V, X, Y, U and So now what we do is just remove, just decrement the flow along this cycle, change 1 to 0. So I will again redraw the same figure. Yes, we have V, U, XYZ, XYZ and T. X, Y, Z and T. So we have edges S to V, X, S to U, V to Y, V to X, Y to U, U to V, X to Y, X to Z, Z to T, Y to T, this U to T, Y to T, Y to T and also U to T. So this is our flow. So just compare, we are creating a new flow, so we follow the path. Whenever we get a cycle, we should set the flow in the cycle equal to 0. That will not affect the maximum flow because flow out of S is still 3. We get a new flow and it will also have the same number of disjoint paths. So what we have done is just set this flow as 0 along this cycle. Rest is identical. So we make along this cycle, we make the flow as 0. Rest are 1 as before, no change in others. So this way we avoid the cycles in the flow. Now again we proceed with the same idea. Start from S. So we move to V and we have the flow flow along the cycle, we have reduced it to 0. So now this is also 1. Just follow along Y and T. So we get this first disjoint path, ST disjoint path we get is S, V, Y, T. This is first path. So once we have done this, we can again reset the flow as 0 and again repeat the same process. So just for simplicity and to save my time and space, I will modify them here itself. So just change this flow as 0 along the ST path that we have selected. Again repeat the same process. So next we can take like S to X, Z and T, S to X, Z and T, X, Z and T. We take this and once again we just decrease the float along the path to 0. Again repeat the same process. Now the remaining is SUT, SUT. Again same process, make it 0. So we are getting 3 disjoint ST paths. It is very easy to verify. If we mark them SVYT, SVYT, SVY, and then T. First disjoint path. Actually, we can make a label like, just put the label 1 to distinguish between different paths. Next is SXZT. SX, second path, SX, Z, SX, Z, and T. Now third path is SUT. SU, third path, and T. Now we can easily see no edge is reused. So now the same example we'll take once more, but with undirected edges, and see how we solve the same problem. So next, again same. So this was for directed graph. Here we have taken directed graph. Now we'll take undirected graph. The same graph with undirected edges. Undirected graph. Same graph we'll take, but with undirected edges. S, V, U, X, Y, Z, and T. Now all edges are undirected. So S to V, U, and X, V to U, X, and Y, U to Y and T, then X to Y, and Z, Z to T, Y to T. So this is undirected version. Now very simple transformation we have to do. Just simply replace each undirected edge with a pair of directed edges in opposite directions and solve the same problem. So now again we redraw this, create a directed version. Once again, S, V, U, X, Y, Z, and T. Now we have a pair like this, S to V, S to X. Then S to U. Then we have V to X, V to X, V to U, V to Y, then X to Z, X to Y, Y to T, Z to T. Then we have remaining Y, U to T. So this is directed version of the undirected graph. We have created a pair between each edge, and one missing edge is Y to U. Now we start with S and find a path to T. So here also we have several possibilities. Like we can start from S, move to X, Z and T. So just to show how how to remove loop like this pair. So we'll choose a path. We'll try to choose a path, possibly different paths, so that a loop is made, and see how we can avoid it. So just starting from S, SXZT, we choose this path. And then augment the flow by 1. So this is our G as well as GF0 with initial flow equal to 0. So first we have chosen S, X, Z and T. So I will show here 1 SX, Z and T. I will draw the so we have to draw the residual graph also. So again, for just to save my time and space, I will not redraw it, because here there are several edges and making them will take a lot of time. So just imagine, here we can imagine the residual graph. So whenever we have edge with label 1, just assume that we cannot follow that, since it is a backward edge in the residual graph. So this way we'll solve this problem, otherwise it will become too complicated. So next we have to find alternative path, S to T path. So next we can choose like for example S to V we can go, then V to Y and T. So we choose this path, S to V, we can take this X also, S to V to X, X to Y and Y to T. Take this path, S to V we have chosen. We can take V to X we can take, then X to Y we can take, then Y to T. So now next, once again we find simple S to T path, S to U, U to Y we can go, we are S to U to Y, Y to X, X to V, U and T. So we make the path. We are trying to create a loop within a pair. So let's see if we succeed. We have S to U, U to Y, Y to X, and then X to V, then what are the possibilities? We can move to U, then finally to T. So now just imagine the residual graph. We cannot follow edges with flow equal to 1. So all are incoming and outgoing are already occupied. So now there is no ST simple path. So this is the final flow. Final flow value are, again we get value 3. Now how to recover the ST disjoint paths? So again same idea we apply. Just follow along edges with flow 1 and try to get the ST paths. So once again we try, and but here we can see we have a pair. We have a pair x to y and y to x. So this is allowed in this directed graph because these are separate edges. So these are edge disjoint. But if we consider the undirected version, it has a single node, a single edge. So this is not allowed for undirected. So what we have to do, again same idea that we have seen earlier. We have to decrease the flow to 0 along this cycle. So we consider here itself, we follow the path S to V, V to X. Now here we have cycle X to Y and Y to X. We have to make the flow 0 along this loop. So I'll make it here itself to save my time and space. So making them 0 like this. And this will not affect the value of the flow because outgoing flow from S is still 3. And here it again satisfies conservation and capacity conditions because for each x and y, incoming as well as outgoing is 0. So it will not affect conservation condition. Same way here we can see, identify the loop, and we can remove this loop also and get a valid flow which will not affect the value of the flow. So here also we do the same, make them 0 like this. So now we can start finding the disjoint ST paths. So we start from S, move to X, Z and T. So first path we get S, X, Z, T. So just we make them 0 along the path, 0, S, X, Z and T. Next path we find S, U, T. S, U, T. So here also we make them 0, the flow 0, 0, S, U, T. This is also 0. Now last path we find S, V, U, Y, T. S, V, U, Y, T. S, V, U, Y, T. S, V, then U, Y, and then T. Now there is no flow, so we get these 3 disjoint ST paths. Now we can see these paths in the original undirected graph. So first is SXZT. 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 We mark the path labeled 1. Next we have SUT. SUT. We mark it with label 2. SUT. Then third path is SVUYT. SVUYT. U, mark it with 3, SVU, Y and T, Y and T. So now we can see all paths are disjoint, there is no common edge. SXZT, SUT and SVUYT.